This video is about determining the empirical formula of a compound if you know its percent composition by mass. And so we've done the reverse of this, which is to say if we know the formula of the compound, we can determine its percent composition by mass. And so this is kind of the reverse of that. The process is not exactly the reverse, but it's not too difficult to do. So let's go ahead and start in. So if you know the mass percent composition of a particular compound, you can calculate or determine its empirical formula. And the way that this is typically done for the sake of convenience is to say, assume, say, that you've got a 100-gram sample of this unknown compound. And the reason we use 100 grams is because the composition is reported as a percentage. And so if I've got 100 grams of a compound, say, that is 40% carbon by mass, then I know that I've got 40 grams of carbon in that sample because 40 grams is 40% of 100 grams. Now that and it's the same for every other element, now that you have these mass percentages, now that you know the mass percentages, if we're starting with 100 grams, we can just convert that directly into grams of each element. Once we know the mass ratio in grams of each of these elements, we can then divide by their molar masses to convert them into moles of each element. And once we know how many moles of each element are in a 100-gram sample, we can look for a relatively low whole number ratio of their moles. Remember, the mole of one thing always has the same number of entities as the mole of anything else. And so if we know the ratio of moles of elements in a particular sample, that's also going to tell us the ratio of atoms in the formula. And so here is a little roadmap that's from your textbook. We start with the mass percentage of the elements. We assume that we've got a 100-gram sample. That tells us how many grams of each element we have. The next step is to divide, in each case, the mass of the element by the molar mass of that element to give us moles of each element. And then we're looking for a whole number ratio between those numbers, and that gives us the empirical formula. So let's do an example of this. The para-aminobenzoic acid, which is known as PABA, it's a sunscreen. It has the particular property of absorbing ultraviolet radiation. It has the percent composition by mass that I've given to you here. So let's figure out the empirical formula of para-aminobenzoic acid. So it's 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, 23.33% oxygen. And so we say, okay, we're going to assume that we've got a sample of para-aminobenzoic acid that weighs 100 grams. And therefore, we can convert those percentages into masses. So if I've got 100 grams and it's 61.31% carbon by mass, that means I've got 61.31 grams of carbon, 5.14 grams of hydrogen, 10.21 grams of nitrogen, 23.33 grams of oxygen. I can't tell anything by just the ratio of these masses because, of course, each element has a different molar mass. So the mass, 61 grams of carbon, is a different number of moles from 61 grams of oxygen or 61 grams of nitrogen, et cetera. So I've got to convert these things to moles. I'm going to do that by dividing the carbon by its molar mass, 12.01 grams of carbon per mole, 1.01 grams of hydrogen per mole, 14.01 grams of nitrogen per mole, 16.00 grams of oxygen per mole. When I do that, I get a series of numbers that doesn't immediately come out as a series of whole numbers, but there's a little operation we can do to make that happen. First of all, if you just examine these, you can see that to two significant figures, these two are the same thing. And so we're going to assume that these are going to wind up being in a 1-to-1 ratio. You can also just kind of look by inspection and see that, oh, that looks to be half of this, and so these are probably going to be in a 2-to-1 ratio. The simplest thing to do once you're at this point is just to divide everything by the smallest number. And the smallest number here is 0.7288. And so let's see what happens when we take all four of these numbers and divide them by 0.7288. Let's see if that gives us a whole number ratio. So if I take the moles of carbon and I divide by the moles of nitrogen, which was the smallest number there, that gives me a number that to 2 significant figures and almost really to 3 significant figures is equal to 7. If I take the remember we said that we expected the hydrogen and the carbon to be in a 1-to-1 ratio because these two numbers were essentially identical to 2 sig figs. If I divide the hydrogen moles by the nitrogen moles, I get again a number which essentially is 7. Obviously, when I'm for nitrogen, since I'm dividing it by itself, I get 1. And for oxygen, as we said, we expected a 2-to-1 ratio between these two numbers. And when I divide 1.458 by 0.7288, I get 2. And so we can assume that these are there in a molar ratio of 7 to 7 to 1 to 2. And therefore, that becomes the formula for the compound. And so the empirical formula for para-aminobenzoic acid would be C7H7NO2, C7H7N1, so no subscript, O2. And just in case you were wondering if this actually works, I got out my little organic molecule drawing program and drew the structure of para-aminobenzoic acid. And if you count up all the atoms here, you'll see that there are 7 carbons, 7 hydrogens, 1 nitrogen, and 2 oxygen atoms. Okay, that went fairly straightforward because when we did the division, we wound up getting a whole number of everything. Sometimes you won't, and that will require you to, so sometimes when you divide by the smallest number, you're not going to get a whole number in every case. And so that will require you to apply some additional math skills, but not too difficult. And so let's try another example that requires you to do just a little bit more. So hydroxybutyric acid, there's another organic molecule. I'm always going to come in with organic molecules if I can, because that's my thing. But it has the mass percentages that I've listed here. Determine the empirical formula of hydroxybutyric acid. So it's 46.15% carbon, 7.75% hydrogen, 46.11% oxygen. No nitrogen or any other elements in this compound. Just carbon, hydrogen, and oxygen, a real good old-fashioned organic molecule. And so we're going to do the same thing. I'm going to assume that I have a 100-gram sample of hydroxybutyric acid, and that allows me to convert the percentages of each element into grams of each element. 46.15 grams of carbon in a 100-gram sample, 7.75 grams of hydrogen in a 100-gram sample, 46.11 grams of oxygen in a 100% sample. Once more, I'm going to divide these by their molar masses. So the mass of carbon, I'm going to divide by the molar mass of carbon. The mass of hydrogen, I'm going to divide by the molar mass of hydrogen. The mass of oxygen, I'm going to divide by the molar mass of oxygen. That will tell me how many moles of each are in a 100-gram sample. So in a 100-gram sample of hydroxybutyric acid, I've got 3.843 moles of carbon, 7.67 moles of hydrogen, 2.882 moles of oxygen. Well, I need to come up with a whole number relationship among these things, and it's again not super obvious here. And so the place to start, just like we did the last time, is to divide all these by the smallest thing. And so when we do that, when we divide all these things by the moles of oxygen, which was the element there with the smallest number of moles present, we get a whole number for oxygen. Obviously, we have to. But you'll notice here for carbon and hydrogen, we don't get whole numbers. And so now that requires you to use some math skill and take a look at that number 1.333 and say, oh, that is 1 1/3, or as an improper fraction, 4/3. The hydrogen, you ought to be able to look at that and say, oh, that's 2 2/3, which as an improper fraction is 8/3. And then because we're on this theme of having thirds as our denominator, then we would just say that the number 1 is 3/3. Well, now we can just multiply through all of these by 3, and that gives us our elements in a small whole number ratio, 4 to 8 to 3. And so we can write an empirical formula for hydroxybutyric acid, C4H8O3. And again, to prove to you that this actually works and gets you to where you want to, I've drawn a structure out here of hydroxybutyric acid, and if you count up everything here, you will see that there are 4 carbons and 8 hydrogens and 3 oxygens in the formula. The question may arise, where do we actually get these mass percent numbers? And you might say, oh, we get them from the formula, and that's true if you know the formula. But what if you were presented with a substance whose identity you knew nothing about, and you had to figure out what the mass percentages, what elements were present, and what their mass percentages were? Well, that's done by a process known as combustion analysis. That is not something that I'm going to address in this video because it's a little bit more complex. We will do it in class. And so the QOD will simply cover the topics that have been in the previous set of slides, which is determining the empirical formula if you know the mass percent of a compound. Thanks so much.